My name is John Rost. I have a bachelor's degree in physics from Grinnell College in Iowa and a master's degree in mathematics from the University of Iowa. I have also received certification to teach in Iowa and Massachusetts, where I currently live. I have been teaching high school math since 1996 and have taught every class from pre-algebra to advanced placement or AP calculus and statistics, as well as international baccalaureate or IB higher level mathematics or HL math. My students have been very successful on their external assessments, be it AP tests, IB scores, SAT scores, etc. Over the years, I have challenged myself to find new ways to teach math, not relying on the way I was taught, or even the way I understand the topics I'm teaching, coming up with deeper understandings, relying on first principles, and occasionally discovering little tricks that help students understand or remember certain methods or content. I have experimented and tweaked my lessons and continue to do so, and I want to share some of my findings and thoughts about teaching math in high school. This is a quick overview of my general philosophies, and I've made and will continue to make short videos on specific topics. I try to keep the videos to about 5 minutes long, with the exception of this introductory video. I hope you will find these insights useful. Please feel free to comment with questions or thoughts on the videos. So here are my philosophies about teaching high school math. First, math teachers are models of what a mathematician is and does. I even refer to my students as mathematicians all the time. For example, as a mathematician, you need to do such and such. Or, these are the steps that a mathematician would write down, and these are the thoughts going on in a mathematician's head, which you do not need to write down. I often talk about being a lazy mathematician, by which I mean being concise and efficient. Calling the students lazy mathematicians makes them laugh, but also gets them to think of themselves as mathematicians. Decisions about curriculum, pedagogy, modeling of written and verbal mathematical communication, etc., are driven by our broad understanding of math as a discipline through college and even graduate school. Second, avoid being lazy. Foster good habits. When teaching, don't be tempted to skip any steps. Model the most precise and accurate written work because the students will mimic the teacher's bad habits. I also insist on students being precise and accurate with their written work, and I don't let them get away with improper math grammar and syntax. For example, very early on, I tell my students to always use parentheses around any value that they are substituting into an expression. So in this example, substituting x equals 3 into an expression 2x plus 5 should look like 2 and then parentheses around 3 plus 5. I point out that it is a way to communicate to the reader that I substituted the 3 here. Of course, it is also a way to ensure that the parentheses are there when we need them, such as putting x equals negative 2 into x squared plus 1, which should look like negative 2 in parentheses squared plus 1, not negative 2 squared plus 1. I always use parentheses for substitution, and my students get into the habit as well. 3. Promote better understanding by using first principles. Teach why the math works rather than simply how to manipulate the expressions. This may take a little more time, but it is worth it in the long term. Although it can be tedious, inwardly I appreciate it when my students ask me why. Because it means that they are beginning to grasp that math is a proof-based discipline as opposed to an evidence-based discipline, with some exceptions like probability and statistics. A good example of this is my method for teaching circle-based trigonometry. I can't go into details here, but please watch my videos about this for details. At this point, I will mention that the method I use only requires students to memorize the two special triangles from right triangle trig and new definitions of the trigonometric ratios based on a circle of arbitrary radius. Students do not need to spend countless hours memorizing and then constantly practicing using the unit circle, often with little understanding of what is actually going on. Next, teach the most general method first. After teaching the most general method, show how certain variations may allow for shortcuts. If students learn only one method, let it be the most general one. For example, I teach factoring in the following order. On day 1, I teach the greatest common factor, or GCF, including expressions of this nature, where the b plus c in parentheses is identical. Then I teach grouping for 4 terms, such as expressions that look like this, which relates to GCF because this will be the very first step. Then I teach split the middle term for quadratics with any leading coefficient, which relates to grouping. For more information about this, I encourage you to watch some of the videos I've put together. On day 2, I show how students can factor quadratics with a leading coefficient of 1, which does have a shortcut. Then I teach students how to do the difference of 2 squares, and then possibly other methods and combining methods. Another example of this is the habit I described earlier of using parentheses whenever I substitute, because although it is not always mathematically necessary, there are certain situations where the parentheses matter, and if we always use them, we will have them when we need them. Avoid too much memorization. Don't learn 2 formulas when 1 will do. Avoid formulas altogether when understanding is preferable. This may require teachers to explicitly avoid what they were taught or tricks they have used for a long time in their own work and think about the best way to foster student understanding. For example, I only teach the binomial square formula a plus b squared equals a squared plus 2ab plus b squared. I explain to my students that both a and b can be negative. I explicitly avoid a minus b squared equals a squared minus 2ab plus b squared. Textbooks ignore negative a minus b quantity squared or negative a plus b quantity squared. But the first formula is sufficient to take care of all of these cases if a and b may be negative. So I don't teach those options. My treatment of trigonometry is another good example of this principle. Keep this in mind when you watch those videos. I had to completely rethink how I understood trigonometry and look for the first principles underlying the topic. I admit that there are exceptions to this principle. For example, I still teach a cubed plus b cubed and a cubed minus b cubed as 2 separate formulas, because it highlights the fact that you can factor the sum or difference of 2 cubes, but you can only factor the difference of 2 squares. Next, relate topics to each other whenever possible. Connections between topics give students a bigger picture and allow them to practice what they have already learned. They also make the new lessons more accessible. For example, completing the square is an example of using the binomial square formula in reverse. So I teach completing the square as a consequence of the binomial square rather than as a special trick. Most students work out the shortcut on their own anyway. In addition, I chose the order with which I teach factoring carefully so that each new method, with the exception of the difference of 2 squares, uses the previous method. Also, factoring as a whole is related to the distributive property because it is exactly the reverse process. Next, plan for what's coming much further ahead. By this I mean we need to be aware of what students will be learning in math in a few years, either later in high school or even in college. We can make decisions about how we present certain topics in a way that will resemble what they will learn in the future, rather than thinking only about the easiest and quickest way to get through this one lesson now. For example, the binomial theorem describes how to expand a plus b to the n. So teach the binomial square as just a plus b squared, noting that a or b could be negative. Include examples and practice problems with the negatives. Next, teach and explicitly use mathematical vocabulary precisely and accurately. For example, I make a big deal of how terms of an expression are separated by plus signs or minus signs, and I have students count the number of terms in expressions a lot. A few weeks later, when I teach the exponent properties, I make it clear that these rules apply to expressions with one term. So we get a times b quantity squared is equal to a squared times b squared, which is a one-term problem. But a plus b quantity squared is not a squared plus b squared because it involves more than one term. Before we do each exponent problem, we decide how many terms are in the expression to determine whether the properties apply. Finally, the right variety of examples in practice avoids incorrect generalizations. Class examples and practice problems need to include lots of exceptions so students don't generalize incorrectly. This is not always easy to predict, but when I notice students overgeneralizing, I take note and I adjust future lessons to include counterexamples early to avoid this with the next group of students. Eventually, I don't have to fix the error because the students don't have a chance to make incorrect conjectures. For example, with the binomial square, I make sure to have examples where one or both terms have a coefficient and where one or both terms are negative. I also often have non-examples, such as factoring n squared plus 4, which is not quite the difference of two squares, or how you cannot apply the exponent properties to a plus b quantity squared because it involves two terms. I also use different variables once in a while for variety. Thank you for watching this video. I hope you find this one and the others that I've put together useful, and please feel free to comment on them.